Okay, today we will talk about the slope deflection method. We actually briefly did analysis with this method, but let's summarize the main steps. So I'll say the analysis of structures with slope deflection equations. And here I will not say anything different, anything new. I'll just summarize what we were doing. So the solution approach is as follows. The first step is discretization. Right, we will divide the structure into members and node. And then we'll assign degrees of freedom to each nodal point. This is what we have been doing so far. That's the first step, right? The second step is the free body diagram. Draw the free body diagram of the discrete structure right? Show member and moments and shears if required. We will discuss that, okay? Now the third step is slope deflection equations. Right, so write down slope deflection equations for each member. In other words, you represent the end moment in terms of the assigned degrees of freedoms. Okay. The fourth step is the equilibrium equations. Use the free body diagram and write down the equilibrium equations. Now, if you have a rotational degrees of freedom for each rotational degrees of freedom, write down a nodal moment equilibrium equation. This is what we did in our previous example problems. Now, if we have a translational degrees of freedom, write down, or you will be looking for nodal shear equilibrium equation. You can just say that it's not a moment, but you will be looking for a force equilibrium equation at each node. Okay, so basically for each degrees of freedom we will be looking for a equilibrium equation at that node. All right, and of course the fifth step solution. Solve the linear system of equations for unknown degrees of freedoms. Of course, finding the displacement is not enough, right? We have to determine the membrane forces. And 6, we call it usually the post process. Recover the membrane forces. You will just insert the values of the degrees of freedom into slope deflection equations and calculate the support reactions. So basically, this is the general procedure composed of, we can say, 6 steps. And it doesn't matter what type of a structure you have, this is the procedure that we always apply. The most important part is this part. This is the part where we decide how we are going to analyze a structure. Okay? If you make a mistake while assigning a degrees of freedom, if you miss one, then the rest of this solution will be garbage. That's very important. Don't miss any degrees of freedom. If you write more degrees of freedom than required, you may reach to the correct solution, but you will do more calculations. Okay? But the worst thing you can do is to miss or misrepresent a degrees of freedom, because the rest will not be any good. It's just total garbage. And the important thing that you have to remember is, in the slope deflection equations or the slope deflection method is for bending deformations only. So you cannot analyze a truss structure by using a slope deflection equation. Of course, that's very obvious. Why? Because we derive these equations by considering the bending deformation, and this method is again for bending deformation only. We actually did this. We solve a problem where we have only the rotational degrees of freedom, and if you go back to these example problems, you will see that I use nodal equilibrium equation. Now, my next example will be in simple structure where we have both rotational and the translational degrees of freedom. And for each translational degrees of freedom, you will see that we will be using a shear equilibrium equation written at a node. Okay, now let's work on an example problem with the slope deflection method. Now in this example, I have a beam, but half of the beam is stronger than the other half. So I'll just show it this way. So this is 5 meters and 5 meters. And here the inertia is 2 times EI, and the inertia here is EI. And I have a uniform distributed load on this member, which is equal to 10 kilonewton meters. Okay. All right, so let's do the discretization now. Or let's label it A, B, C. So at point A, I have a node. Between A and B, a continuous member. At B, there's a discontinuity. So I have to define a node, right? Because the moment of the section properties change at B. And I have another continuous member at BC. And there's a node. So in this structure, I got 3 nodes and 2 members. Okay. Now let's define the degrees of freedoms. So I have defined that I have a rotation, theta b, and here I define a translational degrees of freedom in the downward direction, delta b. Remember that I don't have to guess the direction of the translation. Okay, I'll just assume that it's in the downward direction. I can analyze the same structure by saying that it's in the upward direction, and at the end of the solution I expect to have a negative value, right? If I assume that it's in the upward direction. Here I chose it in the downward direction because it is obvious and I expect to see a positive result, all right? Now let's draw the free body diagram now. Here I'm really not showing any member local axis or the member directions, but let's say that this is the first member, this is the second member, okay? Because I will not use it. Now let's draw the free body diagram now. I'm using the discrete structure. I have a member AB loaded with a uniformly distributed load. This is 10 kilonewton per meter. Node B, another member loaded with uniformly distributed load again, and node C, and this is 10 kilonewton per meter. Okay. Now let's show the member and forces. So this is a fixed support, so I have a moment. I'm showing all the moments in counterclockwise direction. Why? Because that's the way I drive the slope deflection equations. So everything should be consistent. So MAB, that's MBA. I got MBC here and MCB. These are the end moments. Now I have a rotational degrees of freedom and I have a translational degrees of freedom. So for a rotational degrees of freedom, I'll be looking for a moment equilibrium at point B. And for a translational degrees of freedom, I should be looking for a shear equilibrium at B. So I will be needing the shears also. Let me use a different color for shear, sorry. Okay, so I don't know the actual direction of the shear, I'm just showing that it is in the upward direction. So that's VBA, and again I'm showing it in the upward direction, that's VBC. Now if I transfer those to the nodes, so I have a clockwise moment MBA, a clockwise moment MBC, a downward force VBA, and another downward force VBC at the node. Okay, now I will be needing a moment equilibrium since I have a rotational degrees of freedom. So my first equilibrium equation is sum of moments at B equal to 0. So this gives me my first equation, MBA plus MBC equal to 0. That's my first equilibrium equation. For the second equilibrium equation, there's a translational degrees of freedom. So I have to write the force equilibrium. Sum of forces in y direction should be equal to 0. So this tells me that VBA plus VBC is equal to 0. That's my second equation. Now, as you see, I got two unknowns and I have two equilibrium equation. So the next thing to do is to write down, use slope deflection equations to figure out what MBA and MBC is in terms of these two degrees of freedoms. And then by using these free body diagrams, I can represent VBA in terms of MAB and MBA. Okay, so with this approach, I can actually write VBA and VBC again in terms of theta B and delta B. And since I have two equations, two unknowns, I will be able to solve that problem. Okay, so let's start with the slope deflection equations. Let's start from member AB or member 1. Okay, now remember that our slope deflection equation has a chord rotation and membrane rotations. And again, in our derivation, we assume that the chord rotation is in the counterclockwise direction. So as a starting point, this is what I'm going to do. This is member AB, okay, that's the initial undeformed, right? And according to our definition here, we say that this point will move in the downward direction, okay, because this is the direction of my degrees of freedom. So I'm saying that this is equal to delta B, and according to that definition, I don't have any translation here. The chord rotation is this one, and the angle for the chord rotation is as follows. That's the phi angle, right? So this is a clockwise rotation, but we derive the slope deflection equation assuming that the chord rotation is counterclockwise. So my phi angle becomes equal to minus, because it's a clockwise rotation, delta B divided by length of the member. Okay. Now, if I have defined my degrees of freedom in the upward direction, right, then I would be drawing the figure like this. That will be the delta B, and the phi angle will be in the counterclockwise direction, and in that case, phi would be equal to delta B over L. So this depends on the way we define our degrees of freedom. I define that the translation will be in the downward direction, and I'm defining my phi angle according to this direction. All right. In that case, delta B is in the downward direction, which makes the phi angle as a clockwise rotation, and that's why I put a minus sign. All right. After having determined that, I can calculate what MAB is. So let's write down the equation 2EI over L. Sorry, the EI is 2EI, so I got 2 times 2EI and 2 theta A plus theta B minus 3 times chord rotation plus fixed moment AB. Okay, so if you look at the tables, we put the tables at the OptiClass website, the fixed and moment tables. You will see that if I have a fixed beam and the uniform distributed load. That's the direction of the fixed arm moment, and magnitude is WL square over 12. And that's the direction of moment again. Magnitude is WL square over 12, but the direction of that moment is clockwise. And again, if you look at point A, I don't have any degrees of freedom. It's a fixed support. So I know that the rotation at A is equal to 0. All right. So let's write down the slope deflection equation one more time. So MAB is equal to 4EI over 5 theta B minus 3 times delta B minus delta B over 5 plus 10 times 5 squared divided by 12. And from that I obtain MAB as equal to EI 4 over 5 theta B plus 12 over 25 delta B plus 20.83. That's MAB. Now let's write down MBA. So MBA is equal to 2 times 2EI over 5. I got theta A plus 2 theta B minus 3 minus delta B over 5 and minus 10 times 5 squared over 12. Again, we know that theta A is equal to 0, and my MBA equation is as follows. MBA is equal to EI 8 over 5 theta B plus 12 over 25 delta B minus 20.83. So these are the slope deflection equations for member AB. Now let's switch to member BC and write down the slope deflection equations. So let's first determine the direction of the court rotation. Remember that that's the initial. And we are saying that this point moves in the downward direction, delta B. So according to our definition, that's the deformed configuration. And that's the phi angle, right? And the phi angle this time in counterclockwise direction. Meaning that the phi angle is equal to delta B over 5. No minus signs this time because court rotation is in counterclockwise direction. Now let's calculate MBC. So MBC is equal to 2EI over 5 to theta B plus theta C minus 3 times phi angle plus 5 times, 10 times 5 squared over 12. Now we know that this is equal to 0, phi angle is equal to delta B over 5, and our moment equation is equal to EI parentheses 4 over 5 theta B minus 6 over 25 delta B plus 20.83. And MCB is equal to 2EI over 5 theta B plus 2 theta C minus 3 times phi angle minus 20.83. Again, this is equal to 0. So our final equation will be EI parentheses 2 over 5 theta b minus 6 over 25 delta b minus 20.83. So these are the end moments. But if you come back here, we need to figure out the shear forces also, VBA and VBC. Okay, so let me do it in here. Let's determine what VBA is. So in order to do that, I will be using this free body diagram. I'm taking moment with respect to that point. Then VBA times 5 minus, oh, they are all in the same direction, sorry. VBA times 5 plus MAB plus MBA minus the moment created by this uniform distributed load should be equal to 0. So this tells me that VBA is equal to 1 over 5 minus MAB minus MBA plus 10 times 5 times 5 over 2. Okay, so if you put MAB and MBA into that equation and simplify, we obtain VBA as equal to minus EI 12 over 25 theta b plus 24 over 125 delta b plus 25. And that's the expression for the shear in terms of theta b and delta b. Again, let's repeat. How do I calculate the shear? By using this free body diagram. I take moment with respect to that point, and VBA times 5 plus MAB plus MBA minus the moment due to this 10 kilonewton meter should be equal to 0. So it gives me the following equation, and I inserted what MAB and MBA is and obtain an expression of VBA. Now, in order to calculate VBC, again, I will use the following free body diagram, and in that case, VBC times 5 minus MBC minus MCB minus the moment due to 10 kilonewton meter should give me equal to 0, should give me what VBC is. So let's do that. So VBC is equal to 1 over 5 MBC plus MCB plus 10 times 5 times 5 over 2. And this will give me the VBC equation as EI 6 over 25 theta b minus 12 over 125 delta b plus 25. Okay, so we find out the moments and shear written in terms of the two unknown degrees of freedoms. Now, once we obtain that, now it's time to write down the equilibrium equations. Now, the equilibrium equations, we find that sum of moments at b equal to 0. Summation of these two moments must be equal to 0. So let's write it down. Sum of moments at b equal to 0. This tells me that MBA plus MBC must be equal to 0. And this is my first equation. So if I insert MBA and MBC into this equation, I obtain my first equilibrium equation, which is equal to EI 12 over 5 theta B plus 6 over 25 delta B equal to 0. That's my first equilibrium equation. The second equilibrium equation, sum of forces in y direction at B must be equal to 0. So this tells me that VBA plus VBC must be equal to 0. And if you insert this expression and this one into this equation, we will obtain the following: EI 6 over 25 theta B plus 36 over 125 delta B must be equal to 50. And that's our second equation. Now I have two unknowns and two equations, and I can solve it. Let's do the solution. So I'm just writing in matrix form these two equations. So here EI, I got 12 over 5, 6 over 25, 6 over 25, 36 over 125. Theta B and delta B is equal to 0 and 50. And when you do the solution, when you solve the system of linear equation, we obtain delta B as equal to 189.4 divided by EI, and theta B as equal to minus 18.94 divided by EI. So let's take a look at this problem and see if it makes sense. So I will sketch the deformed shape and see if it's the way I expect. Let's remember the structure. That's a stronger member and the weaker member. Let's draw the wireframe here. So that's the original undeformed shape. And everything is 0 here, everything is 0 here. So at the middle, it moved in the downward direction. It came here, and this magnitude is 189.4 over EI. And here, I have a clockwise rotation. And this is equal to 18.94 divided by EI. So the deformed shape is, let me redraw it one more time. So it becomes difficult without any friction. So we see a deformation like that. Now here we should ask this question: is it make sense to have a deformed shape like this, or in other words, a clockwise rotation here? Now, if we have a uniform beam under uniform distributed load, we expect to see a zero rotation here. Now what will happen? Let's exaggerate. This is a very strong member, like a concrete beam, okay, and I'm attaching a very weak member here, like this, okay. So how does it deform? This will carry very little load, right? And I expect to see a deformed shape of this member as a cantilever. So if it deforms like a cantilever, I would expect to see a clockwise rotation here, which I did. So the numbers and it's maybe difficult to comment about the numbers because we don't know what EI is, but actually we expect to see a clockwise rotation here, and we did. So this solution makes sense. But of course the solution doesn't end here, right? I have to go back and calculate the moments and draw the moment diagram. And when you do that, you will obtain MAB as equal to 96.6 kilonewton meters and MCB as equal to minus 73.9 kilonewton meters. I didn't calculate the moments at the middle, but you can do it if you want. So the free body diagram for the whole member looks like this. I got 10 kilonewton meters here. At point A, I have a counterclockwise moment. So that's a counterclockwise moment, and magnitude is 96.6 kilonewton meters. At point C, I have a clockwise moment. That's a clockwise moment, and magnitude is 73.9 kilonewton meters. And if you want to draw the moment diagram, that will be the sign convention I'm using. Remember that I'm using this sign convention just to draw the moment diagram or write down the moment equation for integration. So that's our member. That's where it goes. Here I have a negative moment. Magnitude is 96.6. Here I have another negative moment. Magnitude is 73.9, and in between I have a quadratic variation. So I expect to see a moment diagram as follows. That's kilonewton meters, that's kilonewton meters, and you can calculate what MBA is and figure out the moment at the middle. So that's mainly it. I mean, it doesn't matter what type of a structure we have, we always follow this procedure. Discretization, free body diagram. For each rotational degrees of freedom, write down the moment equilibrium. Each translational degrees of freedom, write down the shear equilibrium. Then use the slope deflection equations to relate these end moments with the given degrees of freedoms. Use the free body diagrams to write down the shears in terms of end moments, and then shears in terms of the degrees of freedoms. Once you do all, the rest is very straightforward. Just write the equilibrium equations, combine your equations, and obtain your equilibrium equations written in terms of the unknown degrees of freedoms. Solve the system, obtain the unknown degrees of freedoms, put it into the slope deflection equations, and obtain your end moments. If you want to calculate more, you can use the equilibrium equations. And this is structure free. For every structure, you repeat the same procedure. The only thing that will change in a structure is these degrees of freedoms.